at this point, or that he needs to stop at this point, as he has no reference in this direction and no reference in this direction. You see that you have to use two parameters in order to control your engine, let's say to say to the engine, oh, stop, stop, you cannot go higher than this point, or stop, stop, you cannot go higher than this point. You need to control your engine with two parameters that are unavailable. So we are in a critical situation. We could explode the engine in this direction. We could make the engine becoming liquid due to the high temperature, everything's melting at this point, and you do not have any instrument to take this decision, because nobody is measuring the TIT and nobody is measuring the thrust. What will be the solution? The thrust setting parameter. I will show you that in fact the thrust setting parameter, for example the EPR, will in fact replace this and this. So it is quite strange because we cannot measure that. We cannot measure that, and I say I replace both very different parameters, because one is a temperature and the other one is a force. I replace them by a single unique parameter that I call the TSP. Why? Why is it possible that you are proposing such a fantastic solution somewhere? Or is it possible that we have such an opportunity? This is thanks to the reduced variables. Here you will see, with what I will explain now, what power, what reliability, what fantastic availability and opportunity you get with the reduced parameter. I have always said a reduced parameter is a function of two other reduced parameters that I call RP2 and RP1. Okay? So, for example, if I take the situation here, this is the situation where I can call that the thermal limit. Okay? In the thermal limit region, what could I do? Of course, these are different functions always, but I am just taking the, let's say, principle behind what I'm explaining. These are different functions, different constants, etc. What are the parameters that I could take? I could take, for example, the Mach number. And here, what is the parameter that I have? I have the TIT. TIT expressed in reduced variables. So TIT divided, let's say, by TT1, that is equal to TTA in a subsonic aircraft. And here I need another parameter that I will, of course, choose as the thrust setting parameter. I will do the same rationale afterwards with N1 divided by the square root TTA, but I will do that later on. I take the example first of Pratt & Whitney. And what is the situation that I explain? This is when TIT is reaching its maximum value. That is fixed. I don't know what it is, but someone knows in the company what is the limit value. So this is a constant. And so if you take takeoff situation, or if you take go around when you are landing and then taking off again, if you take maximum climb, the second climb gradient, I don't know which condition, this is corresponding to a certain value here. Maybe K, maybe K prime, maybe K accent. For takeoff, it's not the same value as first climb gradient, the second climb gradient, top of climb, I don't know. But this is a fixed value. And so you see that what are you doing? Of course, you need to have experimental values. You need to have 1 point. You need to know at 1 point what is this, what is this, what is this, and what is this. But you can replace, in fact, the situation by a constant. I'm always representing a constant with k or u rho here. And this constant is equal to what? EPR limit multiplied by TTA. You see? I'd say it's a linear function. Maybe it's not exactly linear. I will have different domains with some linear parts. And I'd say it's constant. This is constant, so I put TA there, and you have EPR limit is equal to TTA. So that means for Pratt & Whitney engines, in the thermal limit zone, you see that this is independent of the altitude. We do not have H, we do not have the pressure here present. So the altitude is not playing any role here, and we see that we will have at a given altitude, you will have that the EPR limit is decreasing with the outside air temperature that is increasing. So the pilot will do what? He will look in order to understand what is his limit when taking off. He will receive from the manufacturer or the fuel control system, the FADEC is receiving from an engineer, a limit value of the EPR instead of a limit value of the TIT. And the value that is introduced by the engineer in the software is a value that is decreasing with the increase of the OAT, and that is not function of the altitude. Okay? Not function of the altitude. If you go in the mechanical limit zone, mechanical limit zone, what will you do? You will replace the equation that you have here by F, because now we have a F limit. In reduced variables, this is F divided by delta ambient. It is equal to another constant, another function of the Mach number and the EPR. I consider this as a constant. This is the limit value. Again, I take this as a constant, and you see that you can say that you have an equation that is a constant is equal to the EPR limit multiplied by delta ambient. We see that the OAT is not playing any role, and at a given OAT, what do you see? You will see that when H is increasing, this is decreasing, so the EPR limit is increasing. And you see that you replace this limit that is related to the thrust by the same indicator. The pilot or another system is looking to an indicator that is again the EPR limit, so it doesn't care if it is higher than the FRT or lower than the FRT. He's just looking to an EPR limit, or the control computer of the engine is just looking at the EPR, and he knows that there is an EPR limit for whatever the zone where you are. In this zone, compute it following this. In this zone, compute it following that. In one of the zones, the EPR limit is independent of the altitude, and in the other zone, the EPR limit is independent of the outside air temperature. And if you have one value, 1 point, in this zone, one point in this zone, you can compute all other EPR limit. This one has been computed once for all and measured on a test bench, and then you will just do this equation, because you know the constant here, linear variation of the EPR with the OAT. And so this is what you will have for the Pratt & Whitney engine. For General Electric engine, it will be a bit more complicated. Why is it a bit more complicated? This is because in the thermal limit zone and in the mechanical limit zone, you are defining now TIT divided by TTA is a function, another one, of the Mach number, and now you have N1 divided by the square root TTA. So you see you have TTA that will not be, let's say, to the power 1, and here you will have the thrust divided by delta ambient is another function of the Mach number and N1 divided by the square root TTA. And this is the most complicated case, because here we have the pressure and the temperature. You have the pressure and the temperature. And what are the equations that you can write? Here we have the TT limit. Here we have the F limit. So that will make a N1 limit, and that will make a N1 limit, as I had an EPR limit here. And so FMA again is, let's say, neglected. It's not neglected because you have different constants in function, of course, of the EMA, but what will you have here? You will have N1 limit multiplied by the square root TTA is equal to a constant. And this is independent of the altitude, and at a given altitude you will have that N1 limit will increase with TT, with the OAT that is decreasing. In this case, this is a bit more difficult, because you have an equation like N1 limit is equal to a constant, another constant, and this is N1 limit multiplied by delta ambient, and that is divided by the square root of TT1 or TTA. And you see here that you have different cases with different limits depending on the pressure. So you see that at when the pressure is constant, so the altitude is constant, you see that N1 limit is increasing together with the outside air temperature. And you see that when the outside air temperature is constant, that N1 limit